Hi, my name is Shivani Muthukumar, and my presentation is about the connection between mathematics and origami. Origami is the art of paper folding that originated in Japan. In Japanese, ori means folding and kami means paper. In origami, you can make many amazing 2D or 3D shapes and figures with a single square piece of paper without any cutting or gluing involved. You can create anything from a beautiful swan to a delicate rose. There are so many possibilities. Origami has a strong link to mathematics and can be beneficial to a child's development. I'm going to discuss the connection between origami and geometry, symmetry, the vertical angle theorem, and the Pythagoras theorem by using paper folding visually. I will also cover the golden rectangle and fold a golden rectangle from a square sheet of origami paper without using a ruler. Here are some examples of what you can make using origami. Origami is naturally connected to geometry. In each folded piece of art, when unfolded, we can see basic to complex geometric shapes and patterns. For example, when making a simple fold as shown to the left to create a dog face, we can see different types of triangles such as acute triangles here, and right angle triangles here and here. Symmetry is a term used in geometry that's very much connected to origami. Vertical line symmetry divides a figure into two mirror images. In this picture, you can see the directions to fold an origami heart. There is vertical line symmetry in every step. In the final product, if you draw a line through the middle, you can see that on both sides there is the same shape. When making the swan, we can see vertical and horizontal symmetry. Whether you cut it vertically or horizontally, there will still be symmetry. Vertical angle theorem. Four angles are formed when two lines are crossed. Those angles are opposite to each other, and they are called vertical angles. The vertical angle theorem states that vertical angles are equal. In the picture here, you can see that angles 1 and 3 are equal, and angles 2 and 4 are equal. In the picture to the left, we see a simple paper crease showing the vertical angle theorem. I will also show this in a video I made in the next slide. In this video, I'm going to show you a way to visually see and understand the vertical angle theorem. So first, I fold the piece of paper a few times to get angles when I unfold it. I unfold the piece of paper and I see I have 8 angles. So the vertical angle theorem states that opposite angles are equal. And so here you can easily see that this is true. I'm going to measure 2 of them to prove it for sure. Using the protractor, I see that this first one is 60 degrees, and then I measure the other one opposite to it, and it is also 60 degrees. There you have it, the vertical angle theorem. Angles opposite to each other are equal. Origami proof of Pythagoras theorem. As we all know, the Pythagoras theorem states that if a triangle is a right triangle where A and B are the lengths of the legs and C is the length of the hypotenuse, then A squared plus B squared equals C squared. In other words, the square of the hypotenuse is equal to the sum of the squares of the other two sides. The pictures over here demonstrate that. Proving it with origami. Four right-angled triangles with sides A and B are arranged as shown to the right. They clearly form a square with side length A plus B, which will give the gray area in the middle, which is C squared. The same four triangles rearranged will result in a square with the same side length of A plus B, and now the gray area is split into both A squared and B squared. This proves that A squared plus B squared equals C squared. You can recreate this folding origami paper with color on one side. I did that and I made a video, but due to time constraint, I already folded it. In this video, I'm going to show you how to prove the Pythagoras theorem by using origami. So I folded my two figures from an origami piece of paper like this. One side it has color and one side is blank. These are the two figures. As you can see, this one has four right-angled triangles with side lengths A, B, and C. And in the middle, it's C squared. This square has a side length of A plus B. Now on this figure, it's the same square, but the four
Triangles were rearranged into two rectangles, and c squared was divided into a squared and b squared. If you align these up on top of each other, it's the same shape. And when you go like this, you can see that it lines up perfectly, the a and the b side. This makes the a squared, this makes the b squared, and these two equal this. That's the proof.
Golden rectangle. The golden ratio, also known as the Greek letter phi, is a special number approximately equal to 1.618. A golden rectangle is a rectangle whose side lengths are in the golden ratio, 1 to 1 plus root 5 over 2, which is 1 to phi. In the picture to the right, a divided by b is equal to a plus b divided by a, which is equal to 1.618, which is equal to phi. The golden rectangle is found everywhere, in art, architecture, and more. The golden rectangle can be folded from any square piece of paper. This is a video of me demonstrating how to and proving it.
In this video, I'm going to show you how to make a golden rectangle from a square sheet of origami paper without a ruler or a scale. First, I'm going to label all the points A, B, C, and D, and then we're going to say each side is a unit length of 1. Then we are going to fold the square in half. This makes two rectangles with a width of 1/2. I'm going to label this point F and this point E. Next, we're going to fold from point A to F to make two right-angled triangles. Using the Pythagoras theorem, we can find the hypotenuse of these triangles. It is root 5 over 2. Next, we're going to bisect angle BAF by folding on the bottom edge to the fold we just made. Unfold. The next step is to fold from this point all the way across, backwards, and the resulting rectangle is a golden rectangle. I'm going to label this point H and this point I. Now I'm going to prove that it's a golden rectangle. You can see that line FE is intersected by line AH at this point. I'm going to call it point G. Now we're going to use the bisector angle theorem, which states that line AF over AE is equal to FG over GE. I'm going to call GE x, and since FE is 1, I'm going to call FG 1 minus x. When you solve for x, you get x equal to 1 over 1 plus root 5. We know that triangle AEG and triangle ABH are similar with a scale ratio of 2. BH is twice the size of GE, so BH is equal to 2 over 1 plus root 5. 2 plus 1 over root 5 is also equal to 1 over phi. So now we have a rectangle with sides 1 over phi and 1. If we multiply both sides by phi, then these cancel out and we're left with sides 1 and phi. This is the golden ratio, so this rectangle is golden.
Everything I mentioned in the video is also written here as steps and the explanation, and this is the math part. This paper covered some interesting mathematical connections with origami that are understandable at my math grade level. There are much more advanced mathematical concepts such as origami axioms and geometry constructions which are used when trisecting an angle and doubling the cube. These concepts are beyond my math grade level and I plan to learn them later in high school. In addition to understanding the connection that math and origami share, origami is a fun and relaxing activity. Thank you so much.